You dig a hole at the beach. You use your hands, then a plastic shovel. The sand is warm and dry at the top. Then it gets cooler, damper. Soon, water seeps in and the walls collapse. You've hit the water table. Your hole is maybe 2 feet deep. You feel like you've accomplished something, but curiosity never really goes away. We just scale it up. Instead of a plastic shovel, we use massive multi-story drilling rigs. Instead of digging for a few minutes, we dig for years. And instead of trying to reach the water table, we try to reach something much more ambitious. We try to reach the mantle, the very heart of our planet. So what's the deepest we can possibly dig? The question sounds simple. The answer is not. It's a story about engineering, geology, and the brutal physics of the planet we live on. It's about a Cold War race that had nothing to do with space. And it's about the hard physical limits of our technology against the immense heat and pressure just a few miles beneath our feet. The short answer is about 12.2 kilometers, or around 7.6 miles. That's the record. It's held by the Kola Superdeep Borehole in Russia. That might not sound like much. A 7.6-mile drive is nothing, but pointing that drive straight down changes everything. The distance from the surface to the center of the Earth is about 6,400 kilometers. So, our deepest penetration, our greatest effort, is a mere 0.2% of the way to the center. It's a pinprick, a scratch. To understand why that tiny scratch is such a monumental achievement, you have to understand what happens when you start digging down. And you have to understand the story of the people who did it. The story starts in the Cold War. The Americans and the Soviets were in a race for everything. The arms race, the space race. And a lesser-known race, the race to the Earth's core. The Americans had Project Mohole, an ambitious plan to drill through the ocean floor to reach the boundary between the Earth's crust and the mantle. This boundary is called the Mohorovičić discontinuity, or just MOHO for short. The idea was that the crust is much thinner under the ocean, so it would be an easier target. It was a good idea, but the project was plagued by mismanagement and rising costs. It was eventually canceled in 1966. The Soviets saw their chance. They wanted to prove their technological superiority. They decided to drill on land, on the Kola Peninsula, a remote piece of land in the Arctic Circle. Their goal was to drill as deep as possible, to 15,000 meters, 15 kilometers. They weren't just trying to beat the Americans. They were drilling for science. We knew more about the surface of the moon than we did about the rock a few miles under our own feet. Every theory we had about the Earth's crust was just that, a theory based on indirect evidence like seismic waves. This was a chance to get a direct sample, to literally touch the deep Earth. They started drilling in 1970. The rig they used wasn't what you might imagine. They didn't just drill one continuous hole. They used a main borehole and then branched off from it several times. The final, deepest branch is the one that set the record. It's only about 9 inches in diameter at the bottom, a tiny straw reaching into the abyss. For years, things went smoothly. The drill bit, a complex piece of machinery at the end of a long pipe, would grind away at the rock. They would drill for a few hours, then spend many more hours pulling the entire drill string out of the hole to change the bit, then lower it all back down again. It was a slow, painstaking process, and what they found started to rewrite the geology textbooks. The first surprise was the rock itself. Scientists expected to find a transition from granite to a denser rock called basalt at around 7 kilometers down. This transition, called the Conrad discontinuity, was a standard part of geological models. But they never found it. It was granite all the way down. This suggested that our understanding of the crust, based on seismic waves, was too simple. The change in seismic wave behavior wasn't a change in rock type, but maybe a change in the rock due to intense heat and pressure. A metamorphic change. Then came the water. Scientists were certain there would be no water at these depths. The pressure was too high, the rock too dense. There should have been no pores for water to exist in. But they found it. Lots of it. It wasn't seeping down from the surface. The rock above was impermeable. The theory is that the water, made of hydrogen and oxygen atoms, was literally being squeezed out of the rock crystals themselves by the immense pressure. It was mineral water trapped for billions of years. Perhaps the most amazing discovery was life, or the chemical traces of it. They found microscopic fossils of single-celled organisms, plankton, at depths of 6 kilometers. These fossils were remarkably well preserved, encased in organic compounds that had somehow survived the incredible pressures and temperatures. The rock they were found in was over 2 billion years old. It was a stunning look back into the planet's deep past. By 1983, they had passed 12,000 meters. They were on top of the world. They took a year off to celebrate and upgrade their equipment. But when they started drilling again, they ran into a problem. A 5,000-meter section of the drill string twisted off and got stuck in the hole. They had to abandon that section and start drilling again from a depth of 7,000 meters. It was a major setback, but the real problem, the one that would eventually stop them for good, was the heat. Our planet is hot on the inside. This heat is left over from its formation and is also generated by the radioactive decay of elements in the core and mantle. This heat is constantly flowing outwards. The rate at which the temperature increases as you go down is called the geothermal gradient. The scientists had a model for this. They expected the temperature at 15 kilometers to be around 100 degrees Celsius, 212 degrees Fahrenheit. They could handle that. Their equipment was designed for it. They were wrong. The temperature rose much faster than they predicted. By the time they reached 12 kilometers, the temperature was already 180 degrees Celsius, 356 degrees Fahrenheit. This is hot enough to cook food, to melt some plastics, to make life for machinery very, very difficult. If they continued to their 15-kilometer goal, the models predicted the temperature would be a staggering 300 degrees Celsius, 572 Fahrenheit. This heat is the great enemy of deep drilling. It's not just one problem, it's a cascade of problems. First, the drill bits. They are made of the hardest materials we can create, like tungsten carbide, but extreme heat softens them. They wear out incredibly fast. You spend more time pulling the drill string up and down the hole than you do actually drilling. Second, the electronics. Modern drilling isn't just a dumb spinning bit. It's full of sensors measuring temperature, pressure, rock density, and the orientation of the drill. These electronics can't survive in an oven. The heat fries them. Third, the drilling mud. When you drill, you pump a special fluid called mud down the hole. This mud does several crucial jobs. It cools and lubricates the drill bit. It carries the rock cuttings back up to the surface. And most importantly, its weight provides pressure to counteract the pressure of the surrounding rock, keeping the hole from collapsing. At 180 degrees Celsius, this mud starts to break down. It becomes less effective. The whole operation becomes more dangerous and less efficient. And finally, there's the rock itself. At those temperatures and pressures, rock stops behaving like the brittle solid we know on the surface. It becomes more plastic, more like a very, very thick fluid. It wants to flow. It wants to squeeze the hole you just drilled shut. The pressure is immense. At 12 kilometers down, the pressure is about 4,000 times greater than the pressure at sea level. Imagine the weight of a skyscraper balanced on your thumbnail. That's the kind of pressure trying to crush the borehole from all sides. The combination of unexpected heat and the plastic-like behavior of the rock was the end of the line for the Kola project. The drill string became impossibly difficult to turn. It was like trying to drill through hot taffy with a drill bit made of butter. In 1992, with the Soviet Union having collapsed and funding drying up, the project was officially stopped. The final depth was 12,262 meters. They never reached their 15-kilometer goal. The site is now abandoned, a collection of rusting buildings around a small, welded shut cap on the ground. They're a monument to the deepest hole we've ever dug, and a testament to the forces that stopped us. So, could we do better today? Yes, probably, but not by much. We have better materials for drill bits. We have more heat-resistant electronics developed for things like spacecraft and jet engines. We have more sophisticated drilling muds, but the fundamental physics haven't changed. The Earth is still just as hot, and the pressure is still just as immense. A modern project might be able to push 13, maybe 14 kilometers, but getting to that original 15-kilometer goal would be a monumental challenge, requiring new technologies that don't exist yet. The cost would be astronomical. The German Continental Deep Drilling Program, KTB, which reached about 9 kilometers in the 1990s, faced similar heat problems and cost over $500 million. To really understand the impossibility of going much deeper, we need to take a journey down, past the point where the drill bit stopped. Let's imagine we have a magical, indestructible probe that can withstand any heat or pressure. What would it see on its way to the center of the Earth? The first layer is the crust. This is the thin rocky shell we live on. It's what the Kola borehole was drilling through. On continents, it's mostly granite and is about 30 to 50 kilometers thick. Under the oceans, it's basalt and is only 5 to 10 kilometers thick. Our 12.2 kilometer hole didn't even make it all the way through the continental crust. It's like trying to drill through the skin of an apple and only getting halfway. Below the crust is the mantle. This is the biggest layer of the Earth, making up about 84% of its volume. It's about 2,900 kilometers thick. We've never been there. Everything we know about it is from seismic waves and from chunks of mantle rock that are sometimes carried to the surface by volcanoes. The mantle is made of a rock called peridotite, which is rich in iron and magnesium. The key thing about the mantle is that even though it's a solid, it flows. It churns and convects like a pot of incredibly thick soup simmering over millions of years. The temperatures start at a few hundred degrees at the top and increase to about 4,000 degrees Celsius at the bottom. The pressure is crushing. Any hole we tried to drill here would be instantly squeezed shut. The rock would flow into it as if it were water. Our magical probe would need a powerful propulsion system to push its way through this super viscous solid. After the mantle, at a depth of about 2,900 kilometers, our probe would reach the outer core. And here, everything changes. The outer core is liquid. It's a churning ocean of molten iron and nickel. The temperature is between 4,000 and 5,000 degrees Celsius, hotter than the surface of the sun. The S waves from earthquakes, a type of seismic wave that can only travel through solids, stop dead here. That's how we know it's liquid. This liquid metal ocean is what generates the Earth's magnetic field. As the Earth spins, the moving liquid iron acts like a giant electrical dynamo. This magnetic field protects us from harmful solar radiation. It's essential for life on Earth. But for our probe, it would be an absolute hell. A drill bit wouldn't just be crushed, it would be instantly vaporized. Our magical probe would need to be a submarine capable of navigating a sea of liquid metal at thousands of degrees. No material we know of could survive this. Finally, at a depth of about 5,100 kilometers, our probe would reach the very center of the Earth, the inner core. Here, something strange happens. Even though the temperature is even hotter, around 6,000 degrees Celsius, the inner core is solid. It's a solid ball of iron and nickel, about the size of the moon. How can it be solid when it's hotter than the liquid outer core? The answer is pressure. The pressure at the center of the Earth is almost 4 million times the pressure at the surface. It is so mind-bogglingly immense that it forces the iron atoms to pack together into a solid crystal structure, even at a temperature that should make them a gas. This solid inner core is slowly growing as the Earth cools and parts of the liquid outer core crystallize and freeze onto it. So the journey to the center of the Earth is not a journey through rock. It's a journey through solid rock, then through plastic, flowing rock, then through a sea of liquid metal, and finally to a ball of solid metal hotter than the sun. This is why we can't just dig there. The problem isn't just about making a better drill bit. The problem is that the planet itself fights back with fundamental forces of nature. The heat would melt any machine we send. The pressure would crush it. The very state of matter changes from a brittle solid to a flowing solid to a liquid. Since physical digging is so limited, how do we know all of this? How do we have such a detailed picture of the Earth's interior? The primary tool is seismology. When a big earthquake happens somewhere on Earth, it sends shockwaves or seismic waves through the entire planet. And scientists have seismographs set up all over the globe to record these waves. There are different types of waves, and they behave differently as they travel through different materials. P waves, primary waves, or compression waves, like sound, they can travel through solids and liquids. S waves, secondary waves, are shear waves. They move rock up and down or side to side. They can only travel through solids. By studying which stations receive which waves and how long they take to arrive, we can map out the inside of the Earth. When P waves hit the boundary of the outer core, they bend or refract, creating a shadow zone on the other side of the planet where they aren't detected. And the fact that S waves don't travel through the outer core at all is the crucial piece of evidence that it's liquid. It's like a giant ultrasound for the planet. We can't see inside, but we can build a picture from the echoes. Another way we learn is from volcanoes. Some volcanoes bring up things from deep within the Earth. They can carry chunks of mantle rock called xenoliths to the surface, giving us a direct sample to study in the lab. We also have diamond anvil cells. These are incredible devices that use the tips of 2 diamonds to squeeze a tiny sample of material to pressures similar to those in the Earth's core. By firing a laser at the sample, we can also heat it to thousands of degrees. This allows us to replicate the conditions of the deep Earth in a laboratory and see how minerals behave. So, while our physical reach is tiny, our scientific reach is vast. We have a good model of the planet's interior. But it's still just a model. There are still huge unanswered questions. How exactly does the magnetic field dynamo work? What are the precise compositions of the different layers? How does the inner core interact with the outer core? To answer these questions, people are still dreaming of going deeper. There are no active projects trying to beat the Kola record right now. The immense costs and technical challenges are too great, but scientists are thinking about what it would take. One idea is to move away from conventional drilling. Instead of a mechanical drill bit grinding rock, you could use a probe that melts its way down. A small, heavy capsule made of a high melting point metal like tungsten, possibly powered by a small nuclear reactor, could simply melt the rock in front of it and sink through the crust. This turmoil would be slow, but it could potentially go much deeper than a conventional drill because it wouldn't have the problem of a long, fragile drill string. It could send data back to the surface using acoustic signals or by trailing a fiber optic cable. This is still deep in the realm of science fiction, but it's the kind of thinking needed to overcome the heat and pressure problem. Another avenue is simply better materials and technology. We're constantly developing stronger alloys, more heat-resistant ceramics, and electronics that can operate at higher temperatures. A future drilling project could leverage these advances. Maybe we could use lasers to help fracture the rock ahead of the drill bit, or use smarter autonomous drilling systems that can adapt to the changing rock conditions in real time. But even with these futuristic ideas, the mantle and the core remain utterly out of reach for any physical probe. We may never be able to dig there in the way we dig a hole in the sand. The forces are too great. The deepest we can possibly dig with current technology is probably not much deeper than the Kola borehole. We might be able to add another kilometer or two at enormous expense. To go deeper, we need a fundamental breakthrough in material science or a completely new way of thinking about digging. It can feel a little disappointing. We've been to the moon, we have rovers on Mars and probes flying past Jupiter and Saturn. We've explored the deepest trenches of the ocean, yet the ground right under our feet remains almost entirely a mystery. We are confined to the very thin, cool surface of our world, like microbes living on the skin of an orange, with no way to access the fruit inside. But there's another way to look at it. The Kola Superdeep Borehole isn't a story of failure. It's a story of incredible success. For 20 years, engineers and scientists pushed the limits of what was possible. They drilled deeper than anyone had before, and they made fundamental discoveries that changed our understanding of our own planet. They didn't stop because they failed. They stopped because they discovered the true nature of the Earth. They learned that the planet is far more dynamic, far hotter, and far more powerful than their models had predicted. The real answer to what is the deepest we can possibly dig is not a number. It's a boundary. A boundary of heat and pressure. It's the point where our technology, no matter how clever, is overwhelmed by the raw physics of a planet. We can't dig to the center of the Earth for the same reason we can't fly into the sun. The destination itself is a destructive force, and so we continue to use our other senses. We listen to the rumbles of earthquakes. We analyze the chemical whispers from volcanoes. We recreate the crushing pressures in our labs. We are explorers of a place we can never visit. The deepest hole in the world isn't just a 12.2-kilometer hole in the ground. It's a reminder of the scale and power of the world we live on. In fact, it taught us our limits, and it showed us that some of the greatest frontiers are not in the stars above our heads, but in the ground right beneath our feet.